Okay, here we go. All right, so this is our last topic. I'm going to kind of wrap stuff up. You can also hear how rough my voice is. So I apologize if it cracks like my voice is changing and I'm 13. Right. So I want to wrap stuff up today with some big themes. You know, on the final exam, there will be a question. I'm sorry. There will be a question that will be one of my essay questions for statistics, which, you know, is really just a short answer kind of question. You don't write a long thing, but there will be something like that. So I think this final bit will help you understand that kind of thing, prepare for it. I think you'll be able to see, you'll probably be able to guess the kind of question it will be. Because it's going to be on something that's going to be able to wrap stuff up. So let's actually wrap stuff up. So the first thing is that assumptions are really important. We deal with assumptions all the time in statistics, and the kind of statistics we're talking about in this course these assumptions underlie everything we do. Simple random sample. We violate the crap out of that, but we assume it. We actually can violate it. The math's pretty robust when it comes to the math behind this, when it comes to violation of the simple random sample assumption. So it's fine. It's not a problem. It's not random, okay? A random sample of the population is another one. So not only have a random sample, simple random sample, so it's a simple random sample, and it is a representative of the population. So think about this. In psychology, what we're often doing, let's say we're doing some sort of social process, and we use first-year undergraduate university students. I don't know how representative they are. Sure. They're overwhelmingly female. Right? That doesn't represent the population. They're more educated than the population. Yeah. So if you're thinking about a social process, maybe it's not great. I think a fundamental cognitive process or perceptual process is probably no big deal. But that's about design. In statistics, we're assuming a random sample of the population, probably not. We can violate that too. We're fine. Homogeneity of variance. Ooh, they all need that too. We can violate that to a point. We can violate the crap out of these first two we do every day. And nobody cares. Everything's fine. I once had somebody say, how do you know that the chickadees you study are the same as the chickadees in other parts of the world? And I say, they're just freaking chickadees, man. Pretty sure their memories work the same way if they live in Toronto or Sault Ste. Marie. It's roughly the same. Wouldn't be some fundamental cognitive shift going north 600 kilometers, you know. So. But homogeneity of variance, we can violate that too. Not so much. And the rule of thumb is one group being 4 times more variant than another. But we can violate that. Those are all things we can violate. There's a final one we can't violate, and that's the independence of events. Okay, so if I know Chloe's score, I can't know Andy's score. It doesn't help me. It shouldn't. If it does help me, I have violated independence of events. And the problem is, all the assumptions, all the math behind this assumes independence. And independence is important for calculating probabilities. This is all about probability. So I think it follows that we can't violate that. There are statistical techniques where you can have dependent events, but they aren't the ones we've talked about. By the way, at the conference I was just at, just to let you know that there were a number of talks where people presented data as box and whisker plots. It's become very trendy. I don't know why. But people liked it, and it's useful. So I keep saying you don't use these for yourself. It's becoming popular because you can actually just look and see variance, right? And you can look and see if it's different. They're okay. So just let you know that people are using them. So independent events, don't violate that. You do that, and you're doing it wrong, basically. Here's the final one, and this also. We can't violate this, but it doesn't tend to get, this is related, the error is normal and independent with a mean of 0 and a variance of sigma squared is related to independence of events. That's saying that error is independent, that just means that we have independent events. Because the group that Chloe and Andy are in affects their behavior, and the fact that Andy and Chloe are different people affects their behavior. That's what this is, that's error. But there's nothing in there saying, and also they're sitting beside each other. Right? So independence of events and error being independent, I'm really saying the same thing twice here. But both analysis of variance and regression have all of these assumptions in them. Okay? They all have models. The ANOVA model, I'm just going to go with this sort of vanilla ANOVA, is x equals mu plus tau plus epsilon. Regression model is y hat equals b sub 0 plus b sub 1, x sub 1 plus b sub 2, x sub 2 plus dot 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 plus b sub p minus 1, x sub p minus 1 plus epsilon. So it should look very similar. Shouldn't they? Look at that. If you look at the intercept like a grand mean, which is basically what it is, the intercept is basically the grand mean. Right? That's where everything equals 0. That's where, oh, that's just like the grand mean. Anything before going up or down due to a group. And then we've got error at the end. In the middle is where they're different. But this is just saying all these effects add up. And this is just saying all the effects add up. Sometimes it's just tau, sometimes alpha plus beta, etc. Those are very similar models. And I've said a few times now that ANOVA is just a special case of multiple regression, actually. They both have error. The big difference here is there's no interactions in regression. Can you do it? You can. You can model interactions. It's not easy. It's something that, it's probably something you probably shouldn't do. It's something you probably shouldn't touch because you might get electrocuted. Like, it's something you really need real expertise in doing. People do it, and it's fine, and you can go talk to somebody who's a good stats person, and that may not even be me in this case. Yeah, doing interactions in multiple regressions is not easy. I could probably figure it out what the term should be, but big thing is no interactions, right? That's a big difference between the two. You can do nonlinear relationships in analysis of variance. It doesn't matter, the shape of the curve doesn't affect anything. Shape of the curve doesn't affect anything, okay. So that's a difference too. They have their place. They both have their place. They're both fine. Okay. Questions so far? So you'll see how they're similar. You might start to guess that the question might have something to do with the similarities and differences between multiple regression and analysis of variance. It's pretty obviously it's going to be something along those lines. We make these probabilistic statements at the end, right? We make, it's actually a very cool, when you take a step back, this is really powerful and weird and cool. We make probabilistic statements about how the universe works. That's neat, and we don't know actually how the universe works. So we know how the math works, that's part of the universe. But how does one variable affect another? We don't really know that. If we knew it, we wouldn't have to do the experiments, right? So we do these experiments, we take measures from things that we've measured. They aren't measuring whole populations. And we make probabilistic statements about how likely the world works the way we said it does. You have a chance to have whatever this is I have. Pass. When you have to talk for a living, it's a little difficult. Think about how powerful this is. You need good research. Right? Like you can't do this without good design. You can't make these statements and have any confidence in them without good design. Come back. There we go. So you can't make these statements without good design. This is the point of design is important too. This is why we have you do 2127, we have you do 3286, we have 2 research design classes because of this. And notice how we have 2 research design classes and 2 statistics classes. We think they're both as important as each other. So you can't, if you do statistics without that, you can do anything with numbers. They don't know where they come from. But what if the numbers are collected poorly, it's not going to help anybody. You're not going to prove anything or disprove anything. All you're doing is wasting everyone's time, quite possibly the people's money. Because the people of the country pay for your work. Like, that's how it works. That's the deal. They pay people like me to discover things and teach things. And it's the government that's your money. So you don't want to screw around with that. I take that actually incredibly seriously. That, you know, yeah, did I go away to New Mexico for 6 days and screw around a bit? Yeah, but I also did some work. I was going to say important, how important anything I do is, but I learned some things and taught some things to some other people, right? It's important that we do this kind of stuff and we keep that in mind. So these techniques are great, and you can get a really big head thinking about them, because it's like, I can say how likely it is that this is true. I know things, I have secret knowledge you don't have, which is a cool thing. When you finish your thesis next year, you're going to look at your data, and there's going to be a moment where you know something and no one else in the world knows it. It's a really cool feeling when you go, oh yeah, I know something 8.5 billion people don't know. And it's probably some mundane thing about your thesis, because it will be. And it might be, the thing you know is that I didn't find anything, which isn't that important. But it's a cool thing. The problem is, if you do it with poor research design, these things, when you put numbers on stuff, it gives people a lot of credibility. There's a 95% chance of this, plus or minus this. We're in the middle of an election campaign. We hear about polls all the time. Take a look, when you look at those polls, take a look at how they did the sampling. Take a look at what they talked about. Sometimes they're poorly done. It happens. But when your numbers, like, ooh, precision, and there may not be any precision because you designed it, right? Okay. So the big things, like I said, assumptions and models are probably our biggest things that are really our big overarching themes. Really are that there are models for things. We model things, and those models have assumptions. If those assumptions are broken, then the math doesn't actually really work. That's the thing I think that misses a lot of people. That if the assumptions aren't met, the math you're doing is meaningless. Some of it you can violate, but don't go too far. All right, questions or comments on this stuff? Okay, so I'm going to stop this recording and I'll talk about some other stuff, because I'll talk about one of the questions I put up on the LMS. All right. So we'll do that.